Hey guys, it is Miss Urban, and I'm going to make you your video on how to do the Hardy-Weinberg equilibrium questions from yesterday's instructions within the natural selection tutorial. I know that they have a page in the tutorial that goes over it, but it's still pretty confusing. So what I'm going to do is go over something that we did in the genetics unit. So I'm going to ask you to think back, but we spent a lot of time working on it. I'm going to use that as an example to explain what they're talking about when they talk about calculating like the allele frequencies within a population. So I am going to talk to you guys about sickle cell anemia. We did so many Punnett squares on sickle cell anemia. So I'm going to use the capital A to represent the dominant gene or the dominant trait of normal hemoglobin. Capital S to represent the recessive gene of having sickle cell disease, and AS as the heterozygote. And the reason that I'm using that is one, I used it a lot in class, and two, is because the heterozygous version is like very, very different. An A and an S is the heterozygous version versus like a capital A and a lowercase a, which I think it'll make it clearer when we go through it. So when I start, I'm going to do a heterozygous cross. So it is going to be two people with sickle cell trait having babies and what they get. So this is a cross you should be very familiar with. We have seen it a lot. And let me talk about the Hardy-Weinberg equilibrium with you really quick. First, there's two equations that they give you. P plus Q equals 1. And then P squared plus 2 times P times Q plus Q squared equals 1. So what does that actually mean? Well, the P represents the dominant allele. Okay, an allele is just one version of the trait. So in this case, the P represents the letter A, okay? The A for normal hemoglobin. And in this equation, it's saying P plus Q equals 1. That means that if you take everybody in your population, all your offspring, and you have all the A's, which would be represented by P's, and you add them to all of the recessive alleles, which would be all the S's, you get 100% of the population. And for this, I mean, that is always true. If you take all of the dominant alleles and all of the recessive alleles and add them up, you get 100% of the population. So if you know what P is, you can find Q because you just subtract it from 1. But if you know what Q is, you can find P because you just subtract it from 1. So knowing that P equals the dominant trait and Q is the recessive trait is very important. Now, when we look at P squared plus 2PQ plus Q squared, then you have to know that P squared represents this trait right here. So if each capital A, the dominant trait, is represented by a P, all right, it's just kind of a random letter here. We have capital A. AA would be the same as saying like A times A, which you can write as A squared. That whole box right there is represented by P squared. It's just like there's two of those alleles in that box. 2PQ. So the P, remember if you separated that and did the dominant, and the Q and did the lowercase, it's talking about all of the heterozygous versions. So this was homozygous dominant, and then this one is heterozygous. You have two boxes that each have one dominant and one recessive allele. So there's 2 times P times Q, okay? That represents the other part of the population. And then Q squared is the lowercase guy. So this is just a math equation way of talking about the Punnett squares that we've done so many of, okay? So, okay, let's say that you have 40 people in a population who have normal red blood cells. Say that you have 60 people in a population that have sickle cell trait. And then I'll say that I have 20 people in the population that have sickle cell disease. So this is represented by AA. This is AS, and this is SS. So it's homozygous dominant, heterozygous, and homozygous recessive. So we have to find out, first we're going to calculate what our P number is and what our Q number is so that we can plug in the equation to get the allele frequencies for using the other part. So P is how many A's do we have in this population? So for this one, where we have 40 people, every single one of the 40 people have 2 capital A's. So in order to figure out how many people you have there, you have 40 times 2, which means that we have 80 total letter A. Okay? The next thing that we need to do is, so we still have A's here in sickle cell trait, but everybody with sickle cell trait only has 1 A. So if you have 60 people with sickle cell trait, you have 60 A's. That's it. Okay? So your total number of the letter A is going to be 140 A's total. Okay? Now for the letter S that's your Q. So if we start with the heterozygote version, there's again only one letter S for everybody who's heterozygous. So all 60 people have 1 letter S. And then the sickle cell disease people, they each have 2 S's. So if there's 20 of those people, then you have 40 total S's because it's 20 times 2, which equals 40. So 60 plus 40 equals 100. So when we have the entire population, there are 140 P's and 100 Q's. Now in your problem in the classroom, you have it adding up to a nice 200 number for the total amount of alleles in the population. This one, because I just made up the numbers while we're talking, isn't a nice even number. It is 240 total, 240 total instead of 200. Okay, so if we add the 140 plus the 200, that means there are 240 total alleles. So that is the whole population. So to figure out what percentage P is of that, you have to take how many P's you have, 140, and divide it by the total population, which is 240. 140. So 0.58. I'm going to say 0.58 is the amount for P. Okay. So if you plug that into this equation up here, P plus Q equals 1. It'd be 0.58 plus 1 equals 1. So you could just really quickly take 1 minus 0.58, which you should get 0.42, and that would be your Q. Now, the other way to figure out Q is to take the 100 divided by 240, and it should equal 0.42 also. So you know that you have 58% of the population having dominant alleles and 42% of the population with recessive alleles. And if they want to know how many individuals are homozygous dominant, how many are heterozygous, and how many are homozygous recessive, you have to take those numbers that you figured out for the P and the Q and plug them into the equation. Everything is kind of done separately. So P squared, all right? P squared equals all of the homozygous dominant individuals. And that, for this instance, is equal to the people with normal red blood cells who have the genotype AA. Okay? So in order to calculate that, you take your p-value, which is 0.58, and you square it, or the other way to do that is multiply it by itself. So 0.58 times 0.58. Okay? So once you do that, you're going to come up with your value for p squared. Let me grab a calculator. Should have brought one over here. But so we do 0.58 squared. It's 0.3364. 0.3364. Okay. So .3364. That's my p squared. All I did was take the p-value and plug it into that. So that means that approximately 34% of the population, or 0.33, is 0.336, is going to be homozygous dominant, meaning like 33% of the population has normal red blood cells in the instance of this. Now, to figure out how many of them have sickle cell trait or heterozygous, you would say that equation is 2 times P times Q, which in our instance would be 2 times 0.58 times 0.42. 2 times 0.58 times 0.42 equals 0.4872. Okay, bring that over. Which would equal 2PQ, which is the heterozygous form. Okay? This is, and Q squared, which would be sickle cell disease. So it's, again, this was almost 49% of the population with sickle cell trait in the numbers that I made up. Now, for the sickle cell disease, you're going to want to do the same thing that you did with the homozygous dominant, except you're using the 0.42 number. So that's Q squared is the homozygous recessive. Which in our instance would be sickle cell disease. And represented by the genotype SS. And in order to calculate that, you take the number Q, which we've calculated at 0.42, and square it or multiply it by itself twice. 0.42 squared is 0.1764. 0.1764. So if that's Q squared, which is about 17% of the population, maybe 18% if you're rounding, okay? That we have to see, we have to check our work. If our numbers make sense, if they account for the entire population, then it's going to add up to 1. When we add all these decimals up together, it is going to equal 1, which would equal 100% of the population. So we have, go back to this original equation, P squared plus 2PQ plus Q squared equals 1. So if we said P squared was 0.3364 plus 2PQ was 0.4872 plus Q squared was 0.1764, that should equal 1, okay? And if it does not equal 1, then we did it wrong. And so it does equal 1. I didn't do the calculator because I added it in my head. And you can use a calculator to check my work if you want to, but it does add up. So that's what you would do. When you answer the question, after you do it, you would say that, 33.6% of the population is homozygous dominant, 48.7% of the population is heterozygous, and 17.6% of the population is homozygous recessive. And those are the allele frequencies within the population. All you're doing is using P's and Q's. That is the only thing that is different. We have been working with genetics and Punnett squares and the percentages this entire time, so that should not be anything different. Hopefully this helped a little bit with what they're explaining. And for your question, I think it's on page 13 or so of the tutorial. And so if you follow the same example, but plug in the numbers that they used for the flowers and the flower color, then you should come up with the correct answer. Make sure that you always check your work by figuring out if what you got for your values do add up to 1, okay? And if they do, you're good, okay? Ask me if you have any questions. Bye, guys.